Hello students, welcome to my YouTube channel Learning Mathematics. Today we are going to study the Mobius function. The Mobius function is denoted by mu. Mu of n is given by 1 when n is equal to 1. That means mu of 1 is equal to 1. Mu of n is 0 if n has a square factor. If any square number divides n, then the value is 0. And if no square number divides n, that means if n can be written as the product of primes, all primes have the 1 power, then the value of mu n comes out to be minus 1 raised to power r, where r is the number of primes. We find out some values of mu. For example, suppose we find out the value of mu 30. Now 30 can be written as 5 into 3 into 2. There are 3 prime numbers in 30. So mu of this is equal to minus 1 cube, and minus 1 cube is equal to minus 1. Similarly, if we find out mu of say 5. 5 is a single number. Its value is minus 1 raised to power 1, that is minus 1. What about mu of 40? 4 divides 40 and 4 is equal to 2 square. So a square factor divides 40, its mu value is 0. So this is the mu function. Our first result is mu is multiplicative. What is the meaning of multiplicative function? If m and n are two integers whose GCD is 1, then mu of m into n is equal to mu m into mu n. We prove this result in two cases. If m is equal to 1 or n is equal to 1, then mu of m into n is equal to one number. One number is either it is m or it is n. Suppose we take m is equal to 1, then what is its value? Its value is mu n, that is 1 into mu n, and 1 is equal to mu of 1. It can be written as mu of 1 into mu of n, and what is 1? 1 is also equal to m, so that is mu m into mu n. So any one of them is 1, then the result is same. Again, if any square factor divides m or n, any number, suppose any square number divides m, then mu of m is equal to 0. And if any square factor divides m, then m also divides m into n. So that square factor also divides m into n. So therefore mu of m into n also comes out to be 0. That is 0 into mu n, and 0 is equal to mu m into mu n. Mu m into mu n is also 0. So mu of m into n is 0. Therefore the result is true. So our last case is if both have no square factor. M does not have any square factor, n does not have any square factor. That means m can be written as product of distinct primes p1, p2, pr. N can also be written as distinct primes. This is case 1. This is case 2. This is case 3. N is also product of distinct prime, that is q1, q2, qt. Also we are given their GCD is 1. That means no prime number is common in them. All the prime numbers p1, p2, pr, q1, q2, qt all are distinct. So what about mu m? The number of primes is r, minus 1 raised to power r. Mu n, number of primes is t, minus 1 raised to power t. What about mu of m into n? That is mu of p1, p2, pr, q1, q2 up to qt. So the number of primes is r plus t. The value is minus 1 raised to power r plus t. And their product is also minus 1 raised to power r into minus 1 raised to power t. That is minus 1 raised to power r plus t. That is mu m into mu n. So mu function is multiplicative. Next result we are going to prove is F. Merton's lemma. What is F. Merton's lemma? It says summation D divides N, mu D is equal to 1. If N is equal to 1, it is 0 if N is greater than 1. This is an important result for our next results also. So if we prove it in two cases, when N is equal to 1, then summation D divides 1, N is equal to 1, mu D. Divisor of 1 is only 1, so its value is mu of 1. And we have defined the value of mu 1. Mu 1 is 1. So we have proved summation D divides N, mu D is equal to 1 for N is equal to 1. So let N is greater than 1. When N is greater than 1, by fundamental theorem of arithmetic, N can be written as a product of prime numbers p1 raised to power k1, p2 raised to power k2, so on up to pr raised to power kr. Pi's are distinct primes and ki's are greater than equal to 1. So let f of n is equal to summation d divides n mu d. The value we are to prove, summation d divides n mu d, we take it as f of n. So summation d divides n mu d is equal to f of n, and the value of n is equal to this. It is f of p1 raised to power k1, p2 raised to power k2 up to so on pr raised to power kr. Since mu is multiplicative function, so therefore f is also a multiplicative function. We use the multiplicity of f here, f of p1 raised to power k1, f of p2 raised to power k2, because all are distinct primes, their GCD is 1. So f can be broken up for these prime numbers, f of pr raised to power kr. So the value of f of p1 raised to power k1, it is summation, by the definition of f, summation d divides n mu d, summation d divides p1 raised to power k1 mu d. Now the divisors of p1 raised to power k1, since p1 is a prime number, so the divisors are 1, p1, p1 square, so on, p1 raised to power k1. So first divisor is 1, value is mu of 1. Second divisor is p1, so value is mu of p1 plus mu of p1 square plus and so on mu of p1 raised to power k1. This is the sum of mu of d for all divisors d. So we have taken all the divisors. Mu 1 we know comes out to be 1. What about mu of p1? P1 is a single prime number, one prime number, therefore value is minus 1 raised to power 1. Here it is a square. Square factor divides p1 square, therefore mu of p1 square is 0. Again all are the powers after this are greater than 2. So p1 square divides all of them. So all the values are 0. So therefore its value is 1 plus minus 1, that is 0. So f of p1 raised to power k1 comes out to be 0. Similarly we can prove f of p2 raised to power k2 is 0 and all these values are 0. If we take any one, if it is 0 then again the product is 0. So therefore summation d divides n mu d is equal to product is 0, since f of p1 raised to power k1 comes out to be 0. This is the result for n greater than 1. So this is 0 for n greater than 1. This was the result to be proved. When n is greater than 1, then summation d divides n mu d is equal to 0. Summation d divides n mu d is 0 when n is greater than 1. Thank you.